So the next topic is short circuit on a no-loaded synchronous machine. Short circuit, three-phase short circuit on a no-loaded synchronous machine. Before going to that, you must understand what is armature reaction. Okay, the effect of the stator flux on the rotor or main field flux is called armature reaction. Okay, for example, these are the stator slots, let us say, and in between them there is the rotor. This rotor contains the DC field windings which are fed from the DC supply. So let us assume this is the R phase winding, Y phase winding, P phase winding. These are the stator slots. So the black portion is the stator, and then rotor is rotating inside the stator. Okay. Now the direction in which the rotor rotates is the direction of synchronous machine. So in most of the cases, the rotor of the synchronous machine, that is the rotor of the generator, rotates in the clockwise direction. It rotates in the clockwise direction. That's why your phase sequence always you measure in the clockwise direction. The direction of rotation of the rotor decides the phase sequence. If it's rotating clockwise direction, then you have clockwise phase sequence. If it rotates in anti-clockwise direction, then you have anti-clockwise phase sequence. Okay. Now, when you excite the rotor coils with a DC voltage, the flux that is inside the air gap between stator and rotor is constant, because when DC current flows through a conductor, the constant magnetic flux is produced. Okay. But however, when you rotate this rotor at synchronous speed in clockwise direction, this rotor flux or the constant flux that is produced by the DC current flowing through rotor winding also rotates at the synchronous speed in clockwise direction. Let us call this flux as the rotor flux. Rotor flux. Psi R. This is rotor or main field flux. So it is not a fixed flux, but because the rotor is rotating, this flux is also rotating at synchronous speed in clockwise direction. Okay, but the conductors inside the stator, slots are fixed. Okay, these conductors are fixed. So the magnetic field associated with the conductor is continuously changing, but the conductor is fixed. So there is a relative motion between the magnetic field and the conductor. So EMF is induced in this stator conductors. Okay. So what kind of EMF is induced? An alternating EMF is induced. Alternating EMF is induced, which is of the form the cosinusoidal EMF is induced. So because of the cosinusoidal voltage induced in the stator conductors, depending upon the type of load that is connected to this alternator, the cosinusoidal currents will flow through the stator windings. Okay, so because of cosinusoidal EMFs means voltages induced in stator windings. Cosinusoidal currents flow through the stator windings. Okay. So when the cosinusoidal currents flow through the fixed stator windings, Again, a cosinusoidal flux is induced. A cosinusoidal flux is induced. Okay, this flux is called stator flux. This flux is called stator flux. Okay, so because of the currents induced in the stator windings, one more rotating flux is produced, which again rotates in the same direction of the rotor flux. This is called stator flux. Stator, why we are calling stator flux? This is because of the currents, cosinusoidal currents flowing through the stator windings. This flux is generated. This is called stator flux. It also rotates in the same direction as that of the rotor flux, but there is a angle between them. The both fluxes are rotating in the same direction. The angle between them is called delta. This is called power angle or torque angle. This phi r rotating rotor or main field flux will be leading the stator flux by an angle delta in case of a generator. Exactly reverse will happen in case of the synchronous motor. Okay, now what is armature reaction? First, which flux is produced? Rotor flux is produced. First, rotor flux is produced. Why? Because the DC currents flowing through the rotor winding produces a constant flux, and again the prime mover is rotating. This rotor. So because of this DC flux is also rotating. That flux is called rotor or main field flux. This is the first flux that is created. Because of this rotating flux, EMF is induced in the stator windings. EMFs are induced in the stator windings, which again will induce AC currents flowing through this stator windings. Because of this AC currents flowing through the fixed stator conductor, one more flux is generated, that is called stator flux, which is also rotating at synchronous speed in the same direction as that of the rotor flux. Now, armature reaction is the impact of stator flux on rotor or main field flux. This is called armature reaction. Understand? So this armature reaction depends upon the nature of stator currents. So if you connect a load which is purely resistive across the terminals of the alternator, if you connect a purely resistive load, say for example, just look at this image for your understanding. So if I connect a purely resistive load, okay, if I connect a purely resistive load, then the nature of the currents that are flowing are purely resistive currents. So the armature winding carries purely resistive currents. So in this case, the armature reaction is completely cross magnetizing. Okay. Now, if I connect pure inductive loads, then the nature of this armature reaction is purely demagnetizing. Okay. So if I connect the pure capacitor load, then the nature of this armature reaction is purely magnetizing. So depending upon the nature of current that is flowing through the armature windings, the armature reaction will change. Understand? So armature reaction depends on nature of current flowing through stator windings. Flowing through stator windings. Understand? Case 1. For a purely resistive current, okay, now what happens when a purely resistive current flows? Suppose this is the direction of main field flux. This is the direction of main field flux, say shear. Then the rotor flux will be perpendicular to this one. The rotor flux will be perpendicular to this one. This is how the rotor flux will be there. So this will eventually lead to cross magnetizing effect. Cross magnetizing effect. Understand? So this cross magnetizing effect will change the shape of the induced voltage. Okay. For that they use COM poles or other additional thing that your machine sir will teach. Okay. Second one, if the armature windings carry purely inductive currents, then your armature reaction will be the main field flux. Suppose this is my main field flux shear. My armature flux will be, my stator flux will be opposite to this one. This will be opposite. Okay, this is the direction of shear. So it will eventually reduce the flux. That is why it is called demagnetizing. It will cause demagnetizing because it is reducing the overall flux, demagnetizing effect. But however, the magnitude of shear is less when compared to shear, so there will be net resultant main field flux that is present. Okay. Now, when it carries purely capacitive currents, then this is suppose main field flux. Your stator flux will aid, or which will be in the same direction as that of the, your stator flux and rotor flux both are in same direction. They'll add, one will add to the other. This is called a magnetizing effect. Okay. So when demagnetizing effect occurs, your magnitude of induced EMF will reduce. The induced EMF magnitude will reduce. When magnetizing effect occurs, the magnitude of induced EMF will increase. Here, magnitude of EMF induced will decrease. Here, it will increase. So when magnetizing effect occurs in the system, that is when the Ferranti effect will occur. That's why there is a voltage boost in the system when the armature windings carry purely capacitive currents. Understand? So these are the three effects of the armature reaction. One thing which you have to remember is that when the winding carries purely inductive currents, then the stator flux will act opposite, exactly opposite to the rotor flux. Just give me 1 minute. When a dead short circuit occurs at the terminals of the alternator, that is three-phase short circuit occurs, then what will happen? We know that what is the impedance that is limiting the short circuit current? Only the reactance of the alternator is the only impedance that is limiting the short circuit current. Okay, there is no resistor. So a purely inductive current will flow, which is 10 times the magnitude of full load current. Okay, so in these circumstances, the alternator winding carries alternator windings, that is stator windings, carry purely inductive current, which is approximately 10 times the magnitude of full load current. Understand? So 10 times the magnitude of full load current, such a huge amount of inductive current will pass through the alternator stator windings. So what will be the effect? There will be a severe demagnetizing effect. There will be a severe demagnetizing effect will come. Severe demagnetizing effect. Okay. So what happens? This severe demagnetizing effect otherwise would have made the main field flux zero. Why? Because the magnitude of the stator flux in this circumstance is far greater than the magnitude of the rotor flux. Since they are acting in opposite direction, then what would have happened? The main field flux inside in the air gap between stator and rotor would have become zero. Okay, but however, to keep the law of constant flux linkages, to keep the air gap flux constant for a momentary period of time, what will happen? Some DC decaying currents are induced in main field windings and damper windings. Some DC decaying currents are induced in main field windings and damper windings, which generate the flux that will help the rotor flux, that will help the main field flux. Understand? So what happens? You read the first sentence. Under steady state condition, the armature reaction of synchronous generator produces demagnetizing effect, produces demagnetizing flux. So this demagnetizing flux is opposite to main field flux. So how we model this demagnetizing flux in order to explain the demagnetizing flux? That's why we model the alternator as an EMF. So one reactance, this is called XA armature reactance. The other reactance is XL leakage reactance, and this is the terminal voltage. This is the induced voltage, and this is the terminal voltage where the current flowing is armature current, IA. Okay. There is no such physical reactance called XA. Because of the voltage drop that occurs due to demagnetizing effect, to model that voltage drop, we are keeping a reactance called armature reactance. Otherwise, there is no physical reactance. Why leakage reactance is coming? Because 100% rotor flux will not link with the stator. There is a leakage of 2 to 5%. To model that leakage, we are having this XL. So if you add both of them, it would become XT, that is XA plus XL. Leakage reactance plus armature reactions will give you direct axis reactance for a cylindrical rotor machine, Understand? So that is the concept. So how it would become? Terminal voltage is equals to induced EMF minus IA into XD, IA into JXD. Understand? So in terms of circuit, this demagnetizing effect is modeled by a armature reactance XA in series with induced EMF. This when combined with the leakage reactance, here there is a word leakage reactance, it will form direct axis reactance. So when a sudden short circuit occurs, the symmetrical short circuit current is limited only by leakage reactance. Why? Because so when a sudden short circuit occurs, the alternator offers only XL leakage reactance opposite to the short circuit currents. Okay, so there will be severe demagnetizing effect. To oppose this demagnetization of the armature short circuit currents. So to counter the demagnetizing effect of the armature short circuit currents, a DC decaying current appear in field and damper windings that will help the main field flux. Decaying currents appear in field and damper windings that will help the main field flux. These currents decay depending upon the time constant of the circuits. Depending upon the time constant of the circuits, this current will decay. The time constant of damper windings, which has low leakage inductance, is less when compared to the time constant of the field windings, which has high leakage inductance. So, because of this severe demagnetization, the main field flux will suddenly become zero. It would have become suddenly zero. But however, to help the main field flux, a DC decaying currents are induced in the damper windings. So damper windings and main field windings. So damper winding currents and main field winding currents. So the damper winding time constant, the tau is divided as inductance of damper winding divided by resistance of damper winding time constant. So main field winding time constant is inductance of the field windings divided by resistance of the field windings. Here, the time constant of damper windings is very small when compared to the time constant of the field windings. Why? Because LDW is smaller when compared to the LF, inductance of the field windings. So these currents will decay very fastly, whereas this will gradually decay. Understand? That is the concept in this one. So now the synchronous machine will have three different circuit models when a short circuit fault occurs. The synchronous machine will have three different circuit models when a short circuit occurs. The first one is taken immediately when the fault occurs. Immediately when the fault occurs, you have to take this model. Why? Because immediately when the fault occurs, there is a severe demagnetization. To counter this demagnetization, the damper windings and field windings will come to help the main field winding. So here you have a damper windings and field windings XF in parallel with the armature windings. And this is the leakage reactance. So the overall reactance is called subtransient reactance. This is given by leakage reactance, which is in series with the parallel combination of armature reactance, field reactance, and damper winding reactance. Okay, so synchronous machine offers subtransient reactance immediately when the short circuit occurs. We have to consider the subtransient reactance of synchronous machine immediately after occurrence of short circuit. This is the circuit model. Okay, so now if this is the terminal voltage and if this is the armature current that flows, this armature current is called subtransient current. So here it is given by EG double dash is equals to VT plus J into XT double dash into IA double dash. Okay, so the time period for which we have to this circuit is immediately from the occurrence of fault. That is, let us assume at a t equal to 0 the fault occurred, from t equal to 0 plus to 1 cycle. 1 cycle means 20 milliseconds. So some textbooks will say 1.5, some textbooks say 1 cycle. Let us say 1 cycle. So what happens after that 1 cycle? After that 1 cycle, this IDW becomes 0. The current through the damper windings becomes 0. Why? The time constant is very small. Within 20 milliseconds, this current will decay to 0. This damper winding current will decay to 0. So once the current through any element is 0, how you replace? you simply open circuit that element. For any element, if the current is 0, you open circuit it. So after one cycle, your circuit will become this one, where damper windings are open circuited. So this period is called a transient period. This period is called transient period. The previous case, it is subtransient period. Subtransient period. So here, in the transient period, the reactance is called a transient reactance, which is xt dash, which is given by leakage reactance plus parallel combination of armature reactance plus field reactance. Okay, so this is called the subtransient period. The synchronous machine offers a reactance called subtransient reactance. So this is usually for from second cycle to fifth cycle. This will be there. Second to fifth cycle. Okay. So at the end of fifth cycle, even this main field currents, even this currents through the field windings also decay to 0. So again, it will, the armature, the synchronous machine circuit will become again to the steady state, that is XL plus XA, the state before the fault. This is the steady state where you will write the direct access reactance as armature reactance plus leakage reactance. This is called steady state. Understand? So what you have to remember is the synchronous machine has time varying behavior. Immediately after occurrence of fault, it is in subtransient state. After one cycle to fifth cycle, it is in transient state. 5 cycles after occurrence of fault, it will reach the steady state. It will reach the steady state. Understand? So what you have to remember, xt double dash is less than xt dash, which is less than xt. So subtransient reactance is least, then transient reactance is slightly less, and steady state reactance is the high. So the currents that flow, here we are neglecting the DC offset currents, otherwise the analysis will become complex. We are only assuming the symmetrical short circuit currents. So in this analysis, we have neglected DC offset currents, and only we are analyzing the behavior of the symmetrical short circuit current. Why? Because IA double dash is equals to induced EMF divided by XT double dash. Obviously, XT double dash is less, so IA double dash will be highest. Okay, this is called subtransient current. Subtransient current, symmetrical short circuit current. IA dash is given by induced EMF divided by XT dash. This is called a transient current. Transient current. And once the 5 cycles are over, the machine will reach steady state. Then it is called steady state current. Steady state current. Okay. Now, if you analyze the nature of this symmetrical short circuit current, in the subtransient period it is high. You can see in the subtransient period, the value of this symmetrical current is high. Subtransient period is at maximum 1 cycle it is there. 1 to 1.5 cycle subtransient period is there. And after that it is a transient period up to 5 cycles. After that the machine will reach the steady state. The currents will reach the steady state current. Okay. Subtransient period, transient period, and steady state period. Okay. So this is how the magnitudes of the current, symmetrical short circuit current, will vary from subtransient period to transient period, and from transient period to steady state period. Okay, the symmetrical short circuit current of synchronous generator has this waveform. Why? Because the reactance offered by synchronous machine is changing from low subtransient reactance to high steady state reactance from the span of 0 to 5 cycles immediately after occurrence of the fault. Okay. So now, what currents we take for the selection of circuit breaker? Okay. 2 of the circuit breaker ratings which require the computation of short circuit current. So short circuit current is computed to design the mainly two circuit breaker ratings. Two circuit breakers rating. The first one is the rated momentary current. And second one is the rated symmetrical interrupting current or the rated breaking current. Okay. So symmetrical short circuit current. So symmetrical short circuit current is the current that flows immediately after occurrence of fault, that is computed by using subtransient reactance of synchronous machine. So what he's speaking about is speaking about this current. So this first current immediately after occurrence of fault, the current that flows is the first peak of current. So in order to calculate this symmetrical short circuit current, what we have to consider, we have to take the subtransient reactance of the synchronous machine to calculate the symmetrical short circuit current. Okay. Next, momentary current. Momentary current is the first highest possible current that can flow through the breaker, that can flow through the system immediately after occurrence of fault. So we will calculate the symmetrical short circuit current by taking subtransient reactance, and we will multiply with 1.6. Why we are multiplying 60% more? To take care of the DC offset currents. So momentary current is obtained by multiplying symmetrical short circuit current by a factor of 1.6 to account for the DC offset currents. Simply you calculate symmetrical short circuit current and multiply with 1.6. You will get the momentary current. And one more point, while calculating symmetrical short circuit current, you have to take the XT double dash subtransient reactance of the synchronous machine. Only 2 points. Okay. Next, the symmetrical breaking current. The symmetrical breaking current is obtained by multiplying the symmetrical short circuit current by a factor depending upon circuit breaker speed. Why? Because when the fault is cleared, the current at which the fixed contact and moving contact of the circuit breaker gets separated, that is called breaking current. So immediately when the fault occurs, the relay will sense the fault. It will take some time to sense the fault and give trip signal to the circuit breaker. So the time interval between the instant of occurrence of fault, to the time taken by the relay to close the trip coil of circuit breaker, is called relay time. So relay time is what? Suppose at t equal to 0 the fault occurred. So from this the relay time will start. Let us assume it is taking this time. Here at this point the circuit breaker is energized. The trip command is actuated. So this gap is called relay time. Understand? Circuit breaker, trip coil charged. When the trip coil is charged, then it starts separating. So the time interval between the instant of occurrence of fault, that is t equal to 0, and to the time interval where the trip coil of circuit breaker is charged, this is called relay time. It usually takes 30 to 40 milliseconds for the relay to sense the fault. Okay. So within this 30 to 40 milliseconds, my DC offset currents are reduced. They are not at the peak value. They are reduced to some lower value. So depending upon the speed at which the circuit breaker is operated, your multiplication factor changes. Your multiplication factor will change. Understand? Multiplication factor, circuit breaker speed. That means in which cycle the circuit breaker starts separating. Okay. Suppose for the first cycle multiplication factor is 1.6. Okay. Second cycle if it is 1.4. Third to fourth cycle it is 1.2. Fifth cycle it is 1.1. Above 5 it is 1. because after 5 cycles, the DC offset current is also 0. So usually, mainly, circuit breaker will start separating in the 3rd or the 4th cycle. So most common multiplication factor is 1.2. Why we are multiplying with 1.2? To take care of the DC offset current. So we are multiplying the symmetrical short circuit current with a factor, with a multiplication factor, to take care of the DC offset currents. So it depends upon the cycle in which the circuit breaker is operating. 3rd to 4th cycle, 5th cycle, above 5 cycles. 1 cycle means 20 milliseconds. Why? Because at a 50 hertz frequency, 1 cycle will take 20 milliseconds. Understand? So this is how we calculate momentary current. Momentary current is the highest current that flows immediately after occurrence of fault. Symmetrical interrupting current is the breaking current of the circuit breaker, okay, which is less than the momentary current. Read this question and try to answer. Here is a generator. At the terminals of generator, a 3-phase short circuit occurred. So what is asking? What is the ratio of the initial symmetrical short circuit current and the final symmetrical short circuit current that flows through the alternator? Okay. So if you draw the per unit impedance diagram, it is very simple. Alternator has only one series reactance. This is the short circuit. Now, this is 1 at an angle 0. Immediately after occurrence of fault, we have to consider the subtransient reactance, whose value is J0.2 per unit. So, immediately after occurrence of fault, the subtransient current that flows through the synchronous machine is given by magnitude. If I am only taking magnitude, 1 divided by 0.2, this is 5 per unit. This is 5 per unit. Okay. After the transient period, then what will happen? There will be, after the subtransient period, there will be transient period. After that, the steady state period will come, where the circuit will become, in steady state, the circuit will become this one, where this is 1 at an angle 0. The steady state reactance is J1 per unit. Now, the steady state fault current that flows through the armature is given by 1 divided by 1, that is 1 per unit. 1 per unit. So both are the symmetrical short circuit currents. One is the immediately after occurrence of fault, one is the steady state current. So he is asking the ratio of initial and final value of sinusoidal component of short circuit current is. So that is IA double dash divided by IA is what he is asking. That is 5 divided by 1. 5 is the answer. 5 is the right answer. Now this is GATE 2019 question. In the circuit shown below, the switch is closed at t equal to 0. The value of theta, which will give maximum DC offset current at the time of switching is, which will give maximum DC offset current at the time of switching. If you remember yesterday's derivation, you can straightforward tell the answer. Suppose if you don't know the derivation, then we know that the total current that flows in the circuit after switching is given by, what is the formula? K into e power minus t by tau, which is a transient current, plus Vm by mod z into sine of omega t plus theta minus phi. Okay. So from this, what you are going to get? From this, what you are going to get? K at t equal to 0 minus, or at t equal to 0 plus, we know 0 plus I of 0 is equals to 0. If you substitute that, you are going to get I of 0 is equals to K plus Vm by mod z into sine of theta minus phi is equals to 0, which implies k equal to minus Vm by z, or if you take minus n inside the sign, Vm by z into sine of 5 minus theta. Okay, so your DC offset current is maximum when the k value is maximum. When the k value is maximum. So when the k value is maximum, when 5 minus theta is 90 degrees. When 5 minus theta is 90 degrees, this value is maximum. Okay, so for that you have to calculate the value of theta. For that you have to calculate the value of theta. So first you calculate phi value. Phi is given by tan inverse omega L by R. That is phi is equals to tan inverse. Omega value we already know, 377. 377 into L is 10 power minus 2. Why I am writing 10 power minus 2? 10 millihenry. 10 into 10 power minus 3. That is 10 power minus 2 divided by R value is how much? 3.77. So examiner made our life very easy. So this value both are same. So tan inverse 1 it will become. Tan inverse 1 is 45 degrees. So 45 degrees minus theta should be equal to 90 degrees. Then only your k value will be maximum, because this should become 1. That is 5 minus theta will become pi by 2. So then theta value is given by how much?
Minus 45.
Theta value will become minus 45 degrees. So this question they asked in GATE 2019 for 2 marks. Very simple question if you understand the logic. So at the time of switching, he is asking what is the value of theta for which the DC offset current is maximum. DC offset current is maximum when your k value is maximum. That is the next we will enter into asymmetrical fault analysis. The next topic is asymmetrical fault analysis. So what is an asymmetrical or unbalanced fault? If the fault affects all three phases differently, the impact on R phase is different, the impact on Y phase is different, the impact on B phase is different, then such a fault is called unsymmetrical fault or unbalanced fault. Understand? Now, when the system enters into unbalanced operation, no longer your neutral voltage is 0. When the system is unbalanced, no longer your neutral voltage is 0. So the reference for unsymmetrical fault analysis is absolute ground. The reference for the unsymmetrical fault analysis is absolute ground. Ground is the reference. So whenever the power system is balanced, neutral is the reference. If the power system is unbalanced, ground is the reference. Okay. Since the power system network is unbalanced during the fault, the potential of neutral, the voltage of neutral and ground are different. So we have to consider all the impedances that are connected between the neutral and ground. Why? Because now neutral and ground are at different voltages. So any impedance that is connected between the neutral and ground may carry current. So we have to consider them for our unsymmetrical fault analysis. Understand? These are the 3 important points which you have to remember with respect to the unsymmetrical fault analysis. Okay. Next. So this unsymmetrical fault analysis in the till late 18th centuries, how they used to solve? They used to consider R phase separately, Y phase separately, and B phase separately, and they used to draw 3 diagrams and they used to analyze this one. Okay. But however, in 1920, one mathematician called C.L. Fortescue published one IEEE paper in which he stated that any three unbalanced vectors can be resolved, can be decomposed into 3 sets of balanced vectors. So he published an IEEE paper and they accepted. It's a new mathematical concept. One fine electrical engineer, what he did, there he stated the theorem for vectors. This fellow, even our phasors, that we use in our electrical engineering, they also obey vector algebra. How you add two phasors? Similar to the parallelogram law or triangular law of vector addition, you adopt the same measure to add the phasors. So he tried the same idea with the phasors. It worked out. It worked out. From then onwards, the method that is used to solve the asymmetrical faults or unbalanced faults is by using symmetrical components, method of symmetrical components, where here also the idea is same, which we have borrowed from mathematics, is said any three unbalanced phasors can, what are the unbalanced phasors which we can encounter? They may be voltages, they may be currents, or they may be product of current and impedance, which will become voltage drop. So any three voltages, currents, or voltage drops, any three unbalanced voltages, currents or unbalanced voltage drops can be resolved into three sets of balanced voltages, currents, or voltage drops. Understand? So depending upon this mathematical idea, we will do the asymmetrical fault analysis. First of all, what is an unbalanced phasor? So we know that in a balanced system, the phasor sum of three phasors should be equal to 0, and the magnitude of each phasor should be same. Then we call it is a balanced phasor. Similarly, in terms of voltage also, VA plus VB plus VC should be equal to 0, and mod VA, mod VB, and mod VC should be equal to 0. So if both the conditions are satisfied, then we say that our phasors are balanced. If one of the condition is dissatisfied, both the conditions are dissatisfied, then we call them as the unbalanced phasors. Understand? So this is VA, VB, VC. So this is a balanced set of phasors where your mod VA is equals to mod VB is equals to mod VC. And if you add all this, then VA plus VB plus VC becomes 0. So this is a balanced phasors. Same thing you can write in terms of current. Okay. Now any waveform, suppose there is the three voltages are like this. This is VA, VB, and VC. Then this is unbalanced. Then this is a unbalanced phasor set. Balanced phasor set. Understand? Now, what this concept tells that any three unbalanced phasors can be resolved into any three unbalanced phasors can be resolved into three sets of balanced phasors. Understand? The first set is called, let us call this is an unbalanced phasors, VA, VB, and VC. This I can resolve into one balanced set. This is VA1, VB1, VC1. One more set, VA2, VC2, VB2 plus VA0, VB0, VC0. Okay, so this vector, these three unbalanced phasors, I am writing as the sum of three sets of balanced phasors. What is the phase sequence of the original unbalanced phasors? ABC, which is clockwise phase sequence. Clockwise phase sequence. The components which are balanced and which are having the same positive phase sequence as that of original unbalanced phasors, here this set, the first set, we call it as positive sequence components. Positive sequence components. How we are determined? They are balanced. Why? Because the magnitude is same, and even if you add VA1 plus VB1 plus VC1, the phasor sum will become 0, and they are having the same phase sequence, that is ABC phase sequence, as that of original unbalanced phasors. So such components are called positive sequence components. Such components are called positive sequence components. Second, if you observe, here also these components are balanced, that is mod VA2, mod VC2, mod VB2 are same, and if you add the phasor sum of 3, you will get 0. But however, what is the difference? Here what is the phase sequence? It is ACB, that is opposite phase sequence to that of the original unbalanced phasors. That's why these components are called negative sequence components. Okay, they are balanced set, but however their phase sequence is opposite. The third set where there is a 0 phase angle between the three phasors, and all three of them are having same magnitude and 0 phase angle between them, they are called zero sequence components. Okay, so any three unbalanced phasors can be resolved into three sets of balanced phasors. The first set is called positive sequence components, the second set is called negative sequence component, and the third set is called zero sequence component. Okay, just to understand, see here I am writing their orientation can be such that if you add VA1, VA2, VA0, if you add VA1 plus VA2 plus VA0 vectorially, then you are going to get VA. Their orientation and magnitudes will be such that if you add these three, you are going to get this here. And if you add VB1, VB2 and VP0, you are going to get VB. That is, their orientation and magnitude will be such that if you add these three vectorially, you are going to get VB. Similarly, you are going to get VC. Just to illustrate the same concept, if you carefully observe the image, my VA is unbalanced vector. This is my unbalanced vector. Okay, how I have obtained? See, first one is the positive sequence components. For VA1, again I have added. So this is VA1, VB1, VC1. Okay, they can be oriented in any way such that. So for this vector, if you add vectorially, if you add VA1, VA2 and VA0, you are going to get this VA. He has shown in the figure. If you see, this is VA1 for which he has added VA2, VA1, VA2, again for which he has added VA0. So the vector sum of these three is going to give, if you use this parallelogram law or triangular law, you are going to get original unbalanced phasor VA. Understand? This is your VA. Likewise, you will get VB and VC also by adding their respective components. That means for getting VB, you have to add VB1, VB2 and VB0 vectorially, then you are going to get this VB. Likewise, we will get VC. Okay. So if you vectorially add these three components, then you are going to get the original unbalanced phasors. Now we can see again here also you can see these three are balanced. Why balanced? 120 degrees phase angle between each of them, and their magnitudes are same. 120-degree phase angle between each of them, and the second point is their magnitudes are same. Similarly, the negative sequence components are also balanced, the zero sequence components are also balanced, but there is no phase angle between them. Understand? So it is purely mathematical concept. It is purely mathematical concept. Remember simply as a mathematic principle. Okay. The next we'll discuss operator alpha. So alpha is an operator. Alpha is equals to 1 at an angle. Alpha is equals to 1 at an angle 120 degrees is an operator which when you multiply with any phasor with an operator alpha, the magnitude of phasor remains same. The magnitude of phasors remains same, but the phasor rotates in anti-clockwise direction. The phasor rotates in anti-clockwise direction by 120 degrees. The phasor rotates in anti-clockwise direction by 120 degrees. Understand? So alpha is equals to 1 at an angle 120. Alpha square will become 1 into 1 at an angle 240. Why? Because the multiplication will become 1 into 1 and you have to add the phase angles, it will become 240 degrees. Alpha cube will become 1 at an angle 360 degrees. So 1 at an angle 360 means 1 at an angle 0, that is equals to 1. So alpha cube minus 1 is equals to 0. So if I use the formula a cube minus b cube, I can write this as a minus b into a square plus ab plus b square, that is equals to 0. But we know that alpha is not equals to 1. Why? Alpha value is equals to 1 at an angle 120, which is not equal to 1. So this is an absurd. So what is the remaining relationship? Alpha square plus alpha plus 1 equal to 0. This is important relationship. Alpha square plus alpha plus 1 equal to 0. Okay. So alpha is an operator which you multiply with any phasor. It does not change its magnitude, but it will rotate the phasor by 120 degrees in anti-clockwise direction, in counterclockwise direction. And second relationship is alpha square plus alpha plus 1 equal to 0. Okay. If you take an original unbalanced phasors, let us take this is IA, IB, IC. This we can resolve into three symmetrical components we know according to the Fortescue theorem. So let us call this as IA1, IB1, IC1, positive sequence currents, plus IA2, IC2, IB2, plus IA0, IB0, IC0. Just randomly I have written three unbalanced currents as a sum of three sets of balanced currents. Now we know that mathematically, now in this, if you multiply IA1 with alpha, that means alpha into IA1 will become how much? So the magnitude will remain same, but however, the phasor will rotate by 120 degrees. So this phasor will rotate by 120 degrees in this direction. This phasor will rotate in this direction by 120 degrees. So then it will become how much? It will become, when you multiply alpha with IA1, you are going to get IC1. You are going to get IC1. Similarly, again you multiply this one, that is alpha square into IA1 will become how much? Alpha square into IA1. That means you are multiplying twice. So first rotation will make it IC1. Second rotation, that is one more multiplication with alpha, will make it IB1. So it will become IB1. It will become IB1. Okay. So this is this one. Similarly, if you do here, what you are going to get? Alpha into IA2 will become IB2. Alpha square into IA2 will become IC2. Understand? So here there is no multiplication required because all of them are in phase. IA naught equals to IB naught equal to IC naught. IA naught equals to IA naught equal to IB naught equal to IC naught, because all three of them are in same phase. So how we can write? We know that IA unbalanced current IA is equals to IA1 vector sum of IA1, IB1 plus IC1, sorry, IA naught. So let us write in this fashion. Write with IA naught plus IA1 plus IA2. Similarly, I can write IB as IB naught plus IB1 plus IB2. Similarly, IC I can write it as IC naught plus IC1 plus IC2. IC2. Okay. So here, the same things I can write it as IB naught is same as IA naught. So the second term, first term is same. I can write it as IB naught as IA naught. IB1, how I can write? From this relationship, IB1 I can write it as alpha square IA1. Similarly, IB2 I can write it as alpha into IA2. Similarly, when you come to here, IC naught I can write it as IA naught. IC1 I can write it as alpha into IA1 from this relationship. IC2 from this relationship I can write it as alpha square into IA2. Here the first term I am copying exactly same, that is IA naught plus IA1 plus IA2. Okay, so this relationship I can write in the form of a matrix. This relationship I can write in the form of a matrix, that is IA is equals to this one, IB equals to this one, IC equals to this one. I can write in the form of a matrix. IA, IB, IC, the unbalanced currents or phasors as some matrix into IA naught, IA1, IA2. Okay, so this you are going to get first row as ones, first column as ones. This is alpha square alpha 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 square. You can observe carefully, it is exactly. So I am taking IA1, IA naught, IA1, IA2 as this one. So first row will be 1, first column will be 1. This will become alpha square alpha 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 square. Okay. So this is the vector of unbalanced phasors. Vector of unbalanced phasors. This is transformation matrix. Transformation matrix. This is sequence components. Vector of sequence components. So you simply have to remember this either for currents or voltages. Simply you have to remember this transformation. So in terms of voltages, you can write it as VA, VB, VC, where VA, VB, VC are the unbalanced voltages. This has again the same matrix 1, 1, 1, 1, 1, alpha square alpha, alpha, alpha square into the sequence components VA naught, VA1 and VA2. Understand? So every time rather than writing, we can write it as vector of unbalanced, this one is equals to Z into vector of sequence components. Vector of original unbalanced phasors is equals to Z into sequence components. So from this we can write sequence components is equals to Z inverse into original. Sequence components is equals to the inverse of the same matrix into original unbalanced phasors. So if you do that one, you're going to get, if I do this one, the inverse of this is very simple. It will become IA0, IA1, IA2 is equals to, the inverse of this matrix is very simple, just you have to write 1 by 3. And again the first row is 1, first column is also 1, 1. Just you have to interchange the position of alpha and alpha square. It will become alpha, alpha square, alpha into unbalanced this one. That is IA, IB, IC. Okay. So this is Z. This is Z. This is Z inverse. This is Z inverse. Understand? So you have to remember the Z transformation and Z inverse transformation. Okay. What all we have discussed so far is purely mathematical, nothing related with the electrical system. When a three-phase system is balanced, that is when our power system is balanced, it only contains positive sequence components. There are no negative and zero sequence components. There are no negative and zero sequence components. So when our power system is operating in balanced condition, the zero sequence components, negative sequence components are absent. What all the currents that are flowing, what all the voltages that are present, what are the impedances that are present, they are all called as positive sequence components. They are all called as positive sequence components. Okay, sir, I want a proof. This may be true or wrong. Let us take three-phase load that is supplied by a three-phase balanced source. Okay, this is my load that is being fed from three-phase balanced source. So when the system is balanced, it will supply balanced currents. This is IA. Why we are using ABC? ABC is an international standard. RYB is Indian standard. So let us follow international only. Instead of R, I am using A. Instead of Y, I am using B. Instead of B, I am using C. So it is IA, it is IB, 10 at an angle minus 120 current. That is IB. And my IC current is 10 at an angle plus 120. Okay. So for a balanced load, my balanced source is supplying balanced current. So my system is balanced. Now, for these currents, for these original currents, if I calculate sequence components, that is IA0, IA1, IA2, I am trying to calculate the positive, negative, and zero sequence currents for this system. We know that this is equals to 1 by 3 into 1, 1, 1, 1, 1, alpha, alpha square, alpha into the original currents of IA, IB, and IC. Okay, that is what we have learnt in the previous slide that we have erased. Okay, now what are my IA, IB, and IC values? IA is 10 at an angle 0. This is 10 at an angle minus 120. This is 10 at an angle plus 120. So I am substituting balanced currents here. Then according to this statement, I should only get positive sequence current. Remaining current should not be present. So if I calculate IA0, I am going to get 1 by 3 into 10 at an angle 0 plus 10 at an angle minus 120 plus 10 at an angle plus 120. So the sum of 10 at an angle 0, 10 at an angle minus 20, 10 at an angle plus 120 will become what? 0. 0. So my zero sequence currents are 0. Let me see whether my positive sequence currents holds good or not. 1 by 3 into 10 at an angle 0. Alpha means 1 at an angle 120. 1 at an angle 120 multiplied by 10 at an angle minus 120, it will become 10 at an angle 0. Then it is alpha square. Alpha square means 1 at an angle 240 multiplied by 10 at an angle 120, it will become 10 at an angle 360. That I can write it as 0 degrees. So it is going to get only 10 at an angle 0. Only 10 at an angle 0. Similarly, if I calculate IA2, 1 by 3 into 10 at an angle 0 plus alpha square into this one, it's going to become 10 at an angle plus 120. This is going to become 10 at an angle minus 120. So this is again going to become 0. So in a balanced system, what you can observe, in a balanced system, the zero sequence components, zero sequence currents are not there. So when zero sequence currents are not there, zero sequence voltages also will not be there. The negative sequence currents are absent. So negative sequence voltages are also absent. So when voltage and current both are absent, there is no point of having the impedances. So when the power system is balanced, very, very important point, it only contains positive sequence currents, positive sequence voltages, and positive sequence impedances. The no other components will be present. This is a simple proof which I tried to explain. Okay, that is the first important point. Now, as one of our friend read, when our power system is unbalanced, when it is unbalanced, it contains positive and negative. Definitely it will contain both positive and negative sequence components. But depending upon the fault, zero sequence components may be present and may be absent. In few faults, they will be present. In few other faults, they may be absent. They may be absent. So to understand this, again, if we go back, how to create unbalance? Simple. You assume this current is 0. Here there is an open circuit. Some fuse which is present here has blown. So this one phase became open circuited. Now my system is under unbalanced. If you do the same exercise by substituting IC equal to 0, IC equal to 0, what you are going to get? You are going to get all these components as non-zero. As non-zero. This will be non-zero. This will be non-zero. This will be non-zero. That means all three currents will be present. All three currents will be present. Can anyone tell what is the fault which I have simulated here? It is single line open circuit fault. Single line open circuit fault. So in this fault, all the three currents are present. That is positive, negative, and zero sequence. All zero currents, all three sequence currents are present. Understand? Suppose if you open one more line, then it will become double line to open. Again, you do the calculations. You are going to get, again, you are going to get all three currents. Okay. So you remember this point when you have for single line open circuit and double line open circuit faults, all three sequence currents are present. That is, IA0 is non-zero, IA1 is non-zero, and IA2 is non-zero. Okay. For LG and triple LG faults, also the same condition. That is, all three sequence currents are present. Only for triple L fault, there are no zero sequence currents. Zero sequence currents. Understand? So here I am assuming all the systems are properly grounded, then only I am making this conclusion. Once there is no grounding, then zero sequence currents will not flow. Okay. So you will remember this. For single line open circuit and double line open circuit fault, all three sequence currents are present. For LG and LLG faults are also all three sequence currents are present. For double L fault, there are no zero sequence currents. There are no zero sequence currents. So the conclusion is that when power system is unbalanced, it definitely contains positive and negative sequence components, but depending upon the fault, zero sequence components may be present or absent. Zero sequence components may be present or absent. Okay. The third observation is neutral only carries zero sequence currents. The neutral only carries zero sequence currents. Okay. Now, case 1. When power system is unbalanced. When power system is balanced, first case. What is the neutral current is given by? Neutral current is given by IA plus IB plus IC. That is equals to 0. So my neutral current is 0 in when the power system is balanced. Okay. Case 2. Case 2. When power system is unbalanced. So whenever there is unbalance, again neutral current is given by what? IA plus IB plus IC, but now their phasor sum is non-zero. So whenever there is unbalance, you have to write every component as the sum of its sequence component. So I have to write this as IA0 plus IA1 plus IA2 plus IB0 plus. So whenever any term is unbalanced, you have to write that term as a sum of all three sequence components. That is how you have to solve it. IB1 plus IB2 plus IC0 plus IC1 plus IC2. So I have written IA in terms of its sequence components, IB in terms of its sequence components, and IC in terms of its sequence components. Now IN will become, so if I take all IA naughts same, that is IA naught is same as IB naught is same as IC naught, it will become 3 IA naught plus, if I take IA1, sorry, if I take IA1 common, it is going to make 1 plus IA1, IP1 I can write it as alpha square IA1, IC1 I can write it as alpha into IA1 plus, similarly if I take IB1 common, again you are going to get 1 plus alpha square, alpha plus alpha square. Okay, so we know that 1 plus alpha square equal to 0. So your neutral current will become 3 times IA0 plus 0 plus 0. So what is the conclusion? When the power system is unbalanced, or whenever, whatever may be the situation, the neutral current is equals to, neutral current IN is equals to, it is the sum of all three zero sequence currents, or we can simply write it as 3 times IN0. The neutral current is the sum of all three zero sequence currents. So why here it is becoming 0? Because in balanced condition, your IA0 is equals to IB0 is equals to IC0 is 0. When the system is balanced, all three zero sequence currents are 0. That's why your neutral current is 0. But when the power system is unbalanced, the neutral current is the sum of all three zero sequence currents. So neutral only carries zero sequence currents. The neutral only carries zero sequence currents. That is the third important observation. Okay. The fourth important observation is that, just give me a minute, I'll drink some water. The fourth important observation is that the positive and negative sequence currents flow through the conductors both in forward and reverse direction. Okay, that means many people have this doubt. When I write such a system, suppose this is my source. So this is the source, this is the load, so this will be understand. Suppose the current that is flowing from generator, say IA, IB, IC, any current that starts from the source, it should come back to source. Okay, so this current IA after reaching this point, how it will come back to this again, how it will come back to this point? Because anyhow the neutral current is zero. When it is balanced, the neutral current is zero, so it will not come back to this bar. So how this current that is starting from this source will reach the source? That is a question. Okay, many people will think that it will go through ground. No, it will not go. No current will go through the ground apart from zero sequence currents. Understand? So I'll tell you the trick today. Whatever the current that flows and reaches this point, it will return through other two conductors. That is, half of the current it will come to the same point in this fashion, and remaining half will go to this point. Understand? So the current in the forward direction will flow through the conductors. The current in reverse direction, in return path also, it will flow through the conductor. Similarly for IB current, once it reaches here, this IB current will return through the remaining IA and IC conductors. Understand? Why? Because whenever you pass a balanced current, your neutral current is zero. Neutral will not carry any current. So even if you ground here and if you connect ground here, then also the current will not return through the ground. The current then also will not return through the ground, because ground only carries zero sequence currents. Ground and neutral, you blindly remember, ground and neutral only carries zero sequence currents. So what is the path for this balanced positive and negative sequence currents? So positive sequence currents, when they flow, it is a balanced set of currents. When you add all three positive sequence currents, the sum is zero. Even the negative sequence currents, they are balanced currents. When you add all three of them, the sum is zero. So when positive sequence and negative sequence current flow, they flow through the conductors in forward direction, and they return through the conductors. That is the point. Positive and negative sequence currents flow through the conductors both in forward and reverse direction. They will never flow through the neutral, or they will never flow through the ground. Okay. So when the system is carrying positive sequence currents or negative sequence currents or sum of both, then what is there? Whenever it carries the balanced currents, the neutral current is zero. So when the neutral current is zero, neutral voltage is also zero. So when the system is carrying only positive sequence components or only negative sequence components or sum of both positive and negative sequence components, the neutral current and the neutral voltage is zero. That means when it is carrying the positive and negative sequence currents, the power system, the neutral voltage and ground voltage both are zero. Understand? That is the fourth important observation. Next, last observation. Zero sequence currents Again, I'm reiterating. I'm drawing the same thing. I'm simply drawing the source. Zero sequence currents in the forward direction. They flow through the conductors. In the reverse direction, they flow through the ground. Understand? Okay. So this is your IA naught, IB naught, and IC naught. Now, yes, this is grounded neutral. It may ground through solidly or through some impedance. Let us assume some impedance, Zn. So these three currents, IA naught, IB naught, IC naught, once they reach here, that is IA naught, this is IC naught, and this is IB naught. So these three currents, the phasor sum of IA naught plus IB naught plus IC naught is not zero. Why? Because they are same phase, same magnitude. The sum is 3 IA naught. Their sum is non-zero, but their sum is equals to 3 IA naught. This 3 IA naught current will return through the generator. These currents will return through the generator. They will flow through the ground, and from ground, these currents will again enter into the neutral of the source, and they will flow like this. This is how the zero sequence currents will flow. Okay. So zero sequence currents flow through the conductors in forward direction and return through the ground. From the load point, they will enter through load neutral, they will enter into the ground. Again, through source neutral, they will enter into the generator. Okay. For zero sequence currents to flow, there must be a closed path. There must be a closed return path. Suppose here, if I don't ground the neutral of flow, simply I keep the neutral isolated, then there is no closed path for returning zero sequence currents. In this case, the zero sequence currents will not flow at all. Unless there is a closed path to return through ground, then only zero sequence currents will flow. So in this case, if I don't ground either load neutral or if I disconnect source neutral, in both the conditions, the zero sequence currents will not flow at all. Okay. So if there is no closed return path through ground, then zero sequence currents will not flow. Okay. So here, what is the voltage of neutral? Here, what is the voltage of ground? Voltage of ground is absolutely 0 volt. That is the ultimate reference. Now, what is the current flowing through source neutral? 3 times IA naught. So, what is the voltage of neutral? The voltage of neutral becomes 3 times IA naught into Zn. The voltage of neutral will become 3 times IA naught into Zn, whereas voltage of ground is 0. So, for zero sequence currents, the voltage of neutral and voltage of ground both are at different potential. So neutral voltage formula, you remember this, for any fault the neutral voltage is given by 3 times IA naught into neutral grounding impedance, whereas the voltage of ground is equals to 0. So for zero sequence networks, the reference is absolute ground. Understand? So these 5 points are very important for your exam point of view, as well as these points are very important even for industry engineers to analyze how the protection system will work, how the faults are identified, how the faults are